we're going to look at the derivations of the derivative rules. But before we jump into each rule, let's just remind ourselves what we've learned about the derivative so far. And then after we've discussed that, I want to introduce a new perspective that we'll use when we find out our derivative rules through our derivation process. So the first thing, let's draw a graph of some function. We said that the derivative will tell us the instantaneous rate of change at a point. Geometrically, it represents the slope of the tangent line at that point as well. But we've also mentioned before that to express change, we need another point of reference. So if I add in another point, we are able to calculate the rate of change between those 2 points, but when we do that calculation, what we find is what's called the average rate of change. And in order to get the instantaneous rate of change, we must bring those 2 points as close together as we could possibly do. Okay? And when we do that, we are able to calculate the instantaneous rate of change at a point. So if I zoom in on that area of the graph, and as those 2 points, the distance between them starts to close, I get the instantaneous rate of change. Now, between these 2 points, I'm able to calculate the change in the x and the change in the y, right? So we'll call this change in x, change in y. And we know when these points are separated by some amount, the change in x over the change in y is equal to the average rate of change. But as the change in x approaches 0, we get the instantaneous rate of change. And that's where our limit definition for the derivative came in. So let's write that down. So our limit definition for the derivative, so let's say y prime was equal to the limit as the distance between the 2 points expressed as delta x, or the change in the x's, approaches 0, of our average rate of change, or the slope of the secant line between the 2 distinct points, we get the derivative. We use some alternative notation, so I will write that so you can see the parallel between these 2 definitions. Instead of delta x, we originally wrote h, where h represented the horizontal distance between the 2 points. And instead of writing delta y and delta x, we actually wrote out the change in y and the change in x with function notation. So again, that h represents horizontal distance. On the bottom, we just saw h, but remember, originally it's change in the inputs. The inputs were x and x plus h, and through simplification, we can have just h there. Now, we want to introduce a new perspective on what the derivative can tell us. If we know that the derivative is the change in the outputs and the change in the inputs as the change in the inputs approaches 0, we can manipulate this formula and introduce some new notation that will allow us to view this in a new light. So instead of the delta symbols, we're going to now write this as dy and dx. And those d's stand for the differential of y and the differential in x. And what I want you to think about, so these are the differentials. When you see a differential, is this is expressing a very, very tiny change in x or y. Because again, with the derivative, we're looking at an instantaneous rate of change, which would require these 2 points to be very, very, very close to each other, in the sense that when we calculate the change in x or introduce a slight change in the value of x, we're talking about very, very minuscule numbers. So very small change. And when I mean very small, I'm talking extremely small. So not just 1, but some very low percentage of the value of 1. And now, if we take this equation and move dx to the other side, we'll get dy equals y prime times dx. And you might wonder, well, what does that do for us? Well, what this is telling us is that the change in the output, or the differential in y, so remember, this is dealing with our outputs, can be found as a result of making a minor change, or a very small change in the inputs, and it gets scaled by the value of the derivative. So the derivative acts as a scale factor in this equation. So when we make a very small change in the inputs, which is represented by dx, the derivative will act as a scalar and determine what the small change in the outputs will be. And again, this perspective will carry over into higher level mathematics when you can't visualize the slope of a tangent line at a point, okay, when we're working with dimensions outside our visualization ability. So thinking, all right, the derivative is a scalar. It tells me when I make a small change in the input, what is the resulting change in the output? So there is our new perspective, and we will see that used when we go through some of the derivations of the various rules we've introduced in class. Our first rule that we're going to look at is the constant rule. And this doesn't really require much math, but rather an intuition about what the derivative tells us and what we're presented with a constant function. So a constant function is just a horizontal line. And the reason it's called a constant function is because as this graph changes inputs, the value of the outputs does not change at all. It remains constant throughout the domain of the graph. So if the derivative is supposed to represent the rate of change of a function, and my function is just some constant, it would make sense that the derivative is 0. Okay? Again, if the derivative expresses a rate of change, and there is no change at all in the function, well, then the rate of change at any point is 0. So again, that is more of an intuition-based derivation as opposed to a more mathematical-based one, which we will use more moving forward. Now we're going to look at the power rule. The power rule will be used with power functions. And the reason we have to note that, which may seem obvious to some, but we don't want to use this rule with exponential functions, which we'll look at in a later video. And the nice thing about the power function rule is that we can use it when the exponent is any real number. It does not have to be with just some positive integer. So power functions, so something of the form x to the n, where n is just some real number. Okay? Whether that be a fraction 1/2, whether it be an integer of value 2 or -3, okay, all of this can be applied. And the reason why that's important is because we can classify rational and radical functions or reformat them into power functions. Okay, the power rule is arguably the easiest of the rules that require some math to be found. Therefore, it's to our advantage if we can reformat functions into power functions so that we can utilize this rule. Now, into the rule itself. If we have some function in the form x to the n, we can use our limit definition to find out what the power rule is. So let's say the limit as h approaches 0 of x plus h to the n minus x to the n over h. Now, what you will see is necessary is some sort of an expansion or manipulation of what that first parenthesis is. Now, if you perform an expansion, what you'll get is the first term is x to the n. The next term is going to be n x to the n minus 1 times h, and then plus, and as you move down the line, the values of the exponent for x will decrease by 1, and the values of the exponent for h will increase by 1. Now, you'll see why that's important in a second, but it's unnecessary to write the rest of them, but we'll continue as if this went on for a pretty long way. So let's say we now reach n x to the h n minus 1 plus h to the n minus, and then the last term we still have an x to the n over h. Now, you should notice at this point that the x to the n's cancel. Okay? And what's left over, they all have an h term in them. So as I discussed before, now that those first and last terms are gone, the first term has h, and then the value of h is going to increase by 1 as we go along. So each term, or sorry, not the value of h, but rather the exponent associated with h will increase by 1 as we go along. And therefore, if all the terms have an h, it is necessary for us to factor out an h in order to eventually evaluate this limit. And when we factor out the h, there is only one term that remains that does not have an h in it, and that is the first term that's left over after that initial cancellation that I've made. So if we factor out an h, it is only this first term that I'm writing now that does not have an h. All others will still have an h in them. And now I can cancel out the h's from the numerator and denominator. And now I can reevaluate my limit as h approaches 0. And what happens is that all those terms with an h go away. So all that's left is that n times x to the n minus 1. And remember, what does this limit evaluation tell us? Well, it tells us the derivative. So the power rule is expressed there. And again, you can try this for various examples and see that this holds. Like if you replace n with 2, 3, 4, you can even try it with a negative exponent. And what you would have to do is invert the that numerator, x plus h to the n minus x to the n. You would have to make those rational by moving those things to the denominator and working from there, which still requires an expansion. And then when you rework the algebra, you should still get this end result. So this is our power rule. What it's telling us is take your initial exponent, move it to the front, and subtract 1. Right? So move your exponent to the front, subtract 1. That is the power rule, and we can use our limit definition to find that rule. Next, we're going to look at the sum and difference rule. For this, I'll use both perspectives, but first, let's start with our limit definition. So let's say we're trying to find the derivative of two functions that are being added or subtracted. Using our limit definition, let's do the sum, and then all you have to do is replace the plus with a minus if you want to work out the difference rule, but we will do sum for now. Okay, so there's our first limit definition for if we had a sum. We can distribute that negative into that set of parentheses and rearrange so that we get the following. what we can do from here is split that denominator so that we get something that looks like this. Now, taking the limit of a sum of two things can be found by taking the limit of each piece and then adding them together. So we can rewrite this limit. Now, what does this do for us? Well, you should be able to see that this first limit is the limit definition for a function f. Or for the derivative of a function f. So this whole thing is f prime. Over here, you should recognize that this is the limit definition for the derivative of a function g. So this is g prime. So what did we discover? That the derivative of a sum is equal to the sum of the derivatives. So let's write that down. The derivative of a sum is equal to the sum of the derivatives. So if you were to differentiate this expression up top, we would get f prime of x plus or minus g prime of x, depending on whether or not you have a sum or difference. So there's your sum or difference rule using a limit definition. So just using that limit definition and doing some rearranging, you can see that you just get the sum of the derivatives, or the difference of the derivatives. Now let's look at this from the other perspective that I introduced when we see that the derivative acts as a scalar. So let's say we have two branches on a tree. One branch's growth is expressed through a function f of t, and the other branch's growth is expressed through a function g of t. Now, as we have a change over time, these branches grow by some amount, and we will express that amount as d, or we'll call it the change in f of t, and the change in g of t. Now, that is over maybe some extended period of time. But let's say we want to measure the instantaneous rate of change of these branches as we make a very tiny change in the value of t. Well, we expressed at the beginning, when we make very tiny changes, let's express this change as the differential. So we'll change this to d of f of t and d of g of t. So when we make a very tiny change in time, there is a resulting change in the length of each branch. Now, how is the length of each branch determined? Well, we know that the sum of these two changes will be the total change in each branch together. So if we wanted to measure how these branches are changing as a sum, so if we wanted to measure the difference in f of t plus g of t, that's just going to be adding each piece together. As you can see. So if we wanted to measure the change as a whole, we just add each piece together if those green lines express the change. But again, we're trying to find out very small changes as a result of a small change in time. Now you'll notice that these pieces off to the right the differentials in the outputs. Remember, the differentials of the outputs, what we now introduce, can be expressed as the derivative times the differential of the input. So we can think of this as being equivalent to the derivative times the differential of the input. The derivative times the differential of the input. And again, this is using that new perspective that I introduced at the beginning. We said that the differential of the output should be equal to the differential of the input scaled by the derivative. So I can replace that in my equation. So if we make a substitution, for trying to calculate the differential of the sum of each branch together, we can say that that should equal the following. Now, this doesn't quite look like the sum of derivatives, but if we divide both sides of the equation by the differential of the input, we will see we get exactly what we want. What's the only difference between this formula and the formula above? Instead of the variable x, we have a variable t, which expresses time. But nevertheless, our discovery reveals that the sum and difference formula is the same as what we initially found using the limit definition. Now let's look at the product rule. So the product rule will be used anytime we have two functions being multiplied together and we need to calculate a derivative. So let's say we have f of x and we have g of x being multiplied, and we want to differentiate this. The trick to the product rule is to visualize this product as an area formula. Think f being the length, g being the width of some rectangle. The derivative is supposed to calculate some change. Now, as we make a change in the value of x, f and g will both change by some amount. So as x changes, f and g will both change as well because they are functions of x. So f will extend, and we'll call that the change in f of x. And then g will also extend, and we'll call that the change in g of x. Now, we don't want just some long change or some arbitrary change in x, but rather we want some very small change in x so that we can observe what tiny change in f will result from that initial change in x. So rather than delta, let's go back to our differential. Now what happens here is there's this newly formed area. The value of this newly formed area is the expression for the derivative. The newly formed area I've drawn is rather large, but when we talk about differentials, I want you to think that in reality, the newly formed area or the newly added area to this initial rectangle or square, however it's formatted currently, is very, very small. Like we're talking about some rectangles of really, really tiny width. But it's much more visually appealing if we have some thickness to each of these. So just keep in mind that in reality, these are very, very small rectangles that have been added on to the initial rectangle. So if the derivative is supposed to be the calculation of the change, then if we add up the new formed area, that should represent our derivative. So if we were to add that up, what we're going to have is d of f of x times g of x. So remember this. That will give us the area of this rectangle here. If we multiply dg of x times f of x, we'll get the area of that horizontal rectangle below. And then we have this tiny square, which we can see is df of x times dg of x. So let's write that into our derivative formula. And I'm going to write this off to the side so we have more room to manipulate it eventually. We have the difference, the differential for a product of two functions will be equal to this newly added area to our initial rectangle. So again, we thought of the product as an area formula. We drew a rectangle. We made a very, very tiny change in the input, which thus extended f and g by some very, very tiny amount. We made these larger for visual, so it's easier to see what's going on, but just keep that in mind. So what's the newly formed change? It's the newly formed area, so we're going to have df of x times g of x plus dg of x times f of x plus df of x dg of x. But I'm running out of room, so I'm going to rewrite this. Okay, so here's where we are at. Again, using our new perspective of what the derivative can express, we have the differential of the output in multiple locations. The differential of the output can be expressed as the differential of the input scaled by the derivative. So I can rewrite this in my formula as f prime times the differential x times g of x. Actually, I'll write g of x in different color so you can see. Then dg of x, again, the differential of the output can be expressed as the differential of the input times the derivative. We'll add in the original g of x and f of x. And you may be wondering, well, what happens with those two at the end? Well, if you have a differential of two outputs being multiplied together, again, this is where our understanding of what the differential is talking about. These differential values are very, very, very small numbers. So if I multiply very small times very small, this overall value becomes negligible. And therefore, adding it on does not have an impact on the overall derivative. So essentially, it goes away. Now, let's look at, we have the differential. We're trying to find out what the change in the outputs of a product would be. That's what this left side is telling us. Differential of f times g is what is the change in the outputs of a product. We have found that is this new piece to the right. If we divide both sides by the differential of the input, we will see some familiar notation. And this will reveal our product rule. So we can see the derivative, ddx, of a product is equal to the derivative of f times g plus the derivative of g times f. Remember, our mnemonic is left d right plus right d left. There is your product formula. And that is why it is not just f prime times g prime. Now let's look at the chain rule. The chain rule deals with function composition. So we're trying to determine, well, what's the derivative when we have one function within another? Now it's called a chain rule because there's essentially some chain reaction occurring. Let's say we have some value x, 1. This value at x1, if we make a change to that value of x1 so that it moves to some value x2, we have we have caused a change in the value of g as well, because g is dependent on x. So the value of g at x1 will also have some change. How far it changes depends on the function itself, but that will also change to some new value as a result. And if g is changing, well, then the value of f will change by some amount. Again, how much? We are unsure. Depends on what the function expresses. So f will change as a result of g, which will change as a result of x, which is the chain reaction that occurs. Now, we need to be able to come up with an expression for the derivative of a composition that would tell us how this rate of change occurs when we make a tiny change in the value of x. So when we make a tiny change in x, again, sticking with the theme, we're going to call this the differential of x. So again, that is a very, very, very small change. Now, what happens is that as a result, g changes because g is dependent on x. So how do we express the change in g? Well, the change or the differential in our output for g is going to be equal to, recall, the derivative of g times the differential in x. Now, to make this easier for now, we're going to call this piece, let's call this u1, and let's call this u2. So we're going to rename g of x as u, so just some variable u. That way we have f of u1 and f of u2. So u is equal to g of x, but rather than have the composition, now we can just see f as a function of the variable u. So how do we determine the differential of f in terms of u? Well, it's f prime of u times the differential of u. So same approach as g when it was in terms of x. We redefine g as u, so that now instead of f of g of x, I just have f of u, so I don't have to look at that composition. Now we have a way to express the differential in the output of f in just terms of u. But u is not the input variable that we were initially using. We're just using that as a dummy variable for now to easily express the differential for f. So what I can do at this point is resubstitute in for u. So we will have df, and then instead of u, we said u is going to be g of x. So if u is g of x, then du must be d of g of x. But wait, we can do more, because we know how to represent the differential for g of x. To create this line where we have the differential of f composed with g is equal to f prime composed with g times, and again, what's dg of x, but rather g prime of x dx. Now, we divide both sides by the differential for the initial input to the composition, which is dx. And we will get something that looks familiar. And that familiar look will be the formula for the chain rule. So when we take the derivative of a composition with respect to some input variable, in this case x, that derivative will be calculated as the derivative of the outer function, still composed with the inner function, times the derivative of the inner function. Okay, so how did we derive this? Again, we made a small change in the input. The input to our composition was x. that tiny change can be expressed through the differential of x, which is dx. When we made that tiny change to x, g will change as a result. The change in g can be expressed as the differential of g of x. And we said the differential of an output can be written as the derivative of that function times the differential of the input. So again, that was our new perspective. We're just rewriting what the differential of the output could be expressed as. But now, when g of x changes, so does f, because f is dependent on the value of g of x. Now, to make things easier, we redefine g as u. So we could say instead of f of g of x, instead of looking at that composition, we could just call it f of u, so defining f as a function of u. Now we can express the differential of u, or sorry, the differential of f as the derivative of f in terms of u times du. But again, we don't want to use an input variable of u, but rather an input variable of x, so we resubstitute in for u, which we defined as g of x. And you'll see at the end, we had the differential for g of x, which we already established what that equals before, which was the derivative of g times dx. We divide both sides by the differential of the input x to get the derivative formula for a composition. So that is the derivation of the chain rule. And then lastly, the quotient rule. So for the quotient rule, we want to come up with some rule that will allow us to find the derivative of two functions where one is divided by the other. Well, we've already found a rule for the product of two functions, and we've already established how we handle composition. So what I can do is when I see a quotient, we can rewrite this as a product of the numerator times 1 over the denominator, which equals numerator times. Now I don't want 1 over g of x because that's still a quotient, but what I can do is move g of x to the top and express it as a power function. And now, to calculate the derivative of these two things, we can use the product rule. Now, within that product rule, we'll see that there's a composition on this right function, so we'll have to use the chain rule on that. So let's calculate this derivative. So we're going to have left, which is f of x d right. So when I calculate that, it's power rule for the outer function, so move to the front. Keep it composed with the inner function. Subtract 1 from the exponent, and multiply by the derivative of the inside. Plus right d left. Now we're going to have to clean all this up. So any function with a negative exponent, I will move back to the bottom. So we'll have on the left piece before the addition sign, we'll have negative f of x times g prime of x over g of x squared. Plus, we'll have f prime of x over g of x. Now we want to be able to combine these, so I need common denominators. So if I multiply this right expression by g of x over g of x, I'll be able to get a common denominator of g of x squared. So let's simplify that. This will all equal negative f of x. Let's do it in a different color. Now with the common denominators, we can combine. And to avoid a negative out in front, I could write this part first. And there is your quotient rule. The mnemonic we use, low d high minus high d low over low squared. So we could reformat it to fit that mnemonic, but this is also a valid derivative formula for the quotient rule. Again, how is that found? Well, quotients can be rewritten as products. When we reformatted, I moved the 1 over g of x expression into a power function so that I could use power rule when I went through the product rule. And when I used power rule, there was a composition there, which is the trick. You have to notice that. And composition requires chain rule. So those are all the rules. Again, here's your quotient rule that we've discussed so far. And what we should notice is that the operations that are performed between functions really boil down to 3 things. So 3 function operations with derivatives. 1, you could have a sum. 2, you could have a product. Or 3, you could have a composition. Now you may say, well, what about a difference? Well, remember, a difference is just adding a negative. And you could say, well, what about a quotient? And a quotient is just multiplying by a reciprocal. So if we can handle a reciprocal by changing it into a power function, we can use that product rule like I did for the derivation of the quotient rule. And the composition requires chain rule. So if you just ever struggle, just remember you're basically facing 3 operations, sum, product, or composition, and you can work off of that. And when you calculate a derivative, break it down into pieces and work with each piece as if it's its own problem. Just identify which of those 3 scenarios you have. If you know the quotient rule, and you should use that with a quotient. If you do not have a choice of reformatting, because sometimes it can be difficult to try to use a product rule when the quotient rule is staring you right in the face. But that is the derivation of all the formulas that we have looked at so far.